Okay, hello everyone. Really happy to be here at Ray Summit 2023, and I'm excited to showcase our work with Ray. So my name is Harshit, and I'm working as a senior data scientist at LexisNexis. And today I'll be sharing some insights on how we are using Ray to scale our offline batch inference ML pipelines. So this is the agenda for today. So a bit about our company, LexisNexis. So LexisNexis is a legal tech company that enables lawyers, litigators, and attorneys all around the globe to conduct in-depth research and analysis in order to win cases. So our products at Lexis help lawyers in efficiently conducting their research by providing the data and insights they need. Next, I'll talk a little bit about the data science landscape at LexisNexis. So we have access to huge amount of legal data, which is mostly in unstructured format, and we receive from a variety of sources. So to put some numbers, we have around 40 million documents related to law firms where the legal arguments are crafted, around 250 million court-related documents where the outcomes are provided and the legal arguments are tested. And finally, we have about 1.5 billion documents from vendors, and these are mostly third-party external analysts and news publishers. So having the access to huge amount of data, it allows us to run a lot of inferences and do machine learning on it. A few years ago, we recently developed a legal knowledge graph on AWS Neptune that allowed us to uncover complex relationships between different legal entities like plaintiffs, judges, courts, and law firms. And in that way, we were able to provide better inferences and better insights to our customers like lawyers. Machine learning is widely used across LexisNexis, across many domains. And this talk is about one such machine learning use case. And all of these things combined, they power our legal products at Lexis. So next, I'll be explaining about our ML use case, the business aspect of it, the expert witness profiling. So some of you might already be aware that attorneys or lawyers often need to recruit expert witnesses so that they can evaluate claims and testify in courts. Hiring the right expert witness can be can play an important role in determining the outcome of your case. They can make your case more stronger, and they can actually increase the probability for a lawyer to win that case. So it's very important that attorneys hire the right expert witness for their particular case. So how do they do that? So in modern day, an attorney has access to hundreds of experts spread across a variety of fields. So if they have to do it, let's say in a traditional manner, they will have to scan through or read through a lot of legal documents, and these documents and they need to also know what particular expert can comment on for that particular case, or what are the topics and what are the issues they have commented on in the past, so that they can better evaluate that particular expert witness, whether they would be good for this case or not. So, but doing this manually would be like a lot of time-taking process and very not efficient. So we framed this problem into a machine learning use case where we built an automated key phrase extraction pipeline and a clustering pipeline so that attorneys can get the data and insights they need in a very condensed and very refined manner. So this is the snapshot of one of the flagship products called Context. And this is how an attorney would see this screen on their laptops. For example, if they're searching for an expert related to a medical case, let's say two parties are involved in a car accident, and the parties need to hire expert witnesses so that they can make their case more stronger. So in order to search for relevant experts, in this case, they'll need to search through many doctors, and specifically, in which particular field they are experienced in. So as you can see, the attorney can just open this up, the profile of the attorney, of the expert, and they'll be able to see, for example, in this case, this person is an expert in neurological surgery. And if you pay attention to the most discussed facts and subjects, you can see topics and issues this particular expert has commented in the past. For example, this expert can talk about MRI scans, nerve function, physical therapy, and medical malpractice as well. So there are several topics that this expert can comment on. And if an attorney feels like, okay, this seems okay, and this expert is worth more exploration, and so that they can click on the topic, and on the side they would see a relevant document that it would open up, and we will highlight the paragraph in which that topic was mentioned. So the attorneys can proceed in a very granular fashion, and they would this would help us in increasing their efficiency in searching for experts. So that was the basic general idea behind the use case, and this is the high-level overview of our architecture pipeline. It looks like. So we have data lake, and many engineering teams at Lexis subscribe to this, and our team responsible for this machine learning use case, we run a daily job that pulls the relevant data from the data lake and store in S3. We run data cleaning and pre-processing on AWS EMR and using the Spark framework. And the output of this is stored in S3 as a high-quality data set, which is an input to our further machine learning workloads. So next, so earlier we were using SageMaker processing jobs to run our 4 machine learning workloads that builds up our entire pipeline. So I'll talk a little bit about these ML workloads too, so that you guys have a flair of what they are about. So our first ML workload is key phrase extraction and ranking. It uses a large pre-trained model from Spacey. We are also using a third-party library for ranking, and we have also defined a custom scrubber function. Followed by that, we have a data transformation step in which we incorporate a legal domain knowledge and some business logic. And then followed by that, we have embedding-based key phrase filtering step in which we use sentence transform model from Hugging Face. Followed by this step, we have clustering key phrases in which we use hierarchical clustering from scikit-learn library. And the output is stored in S3 bucket. So there are some problems with the existing pipeline. So we observed low CPU utilization across many nodes in the SageMaker pre-processing jobs. Also, inefficient data transfer between S3 bucket and CPU RAM, and no matter how many instances you add up in your SageMaker processing job, we're always limited by the API rate limit, which is 100 MB max. And although SageMaker provides distributed training libraries, but they don't natively support distributed execution of tasks like natively. So if there are distributed training algorithms, you can use that. But for custom transformation, SageMaker doesn't provide easy-to-use APIs. So we found it hard to assign custom number of workers per model or compute resources or to assign custom resources to more granular tasks in an ML workload. Moving from local laptop to production environment was also difficult, and it required several iterations. So all of these limitations combined led to low throughput of our entire pipeline, longer runtimes, and high cost. So we decided to experiment with Ray in order to scale this offline batch inference pipeline, and more specifically, Ray Data API. So this is the updated architecture diagram of our pipeline. And as you can see, we have used Ray for last mile processing. And you can see from this diagram that the first part of the pipeline looks the same. We are using Spark for data cleaning and pre-processing and storing the high-quality data set in S3 bucket. In order to deploy the day cluster, we use very simple Ray launcher API. It's just very easy to use, and we could select the instance type and the number of instances for our custom workloads. And we have used Ray data for these 4 ML workloads that basically define our entire ML pipeline. We started with, so we use the Ray data API for ingesting the high-quality data sets stored in S3. Which are read as a Ray data set, and they are represented as Ray blocks, and each block is stored somewhere in the cluster. Moving ahead, for example, in the case of key phrase extraction and ranking, we use the actor pooling strategy, as we are using the large pre-trained model from Spacey, and it's expensive to set up. Yeah, so as you can see, in the case of Ray, it creates multiple replicas of model in the cluster, and all of these models, they work in parallel, and they do transformation on each block in parallel, thereby reducing the runtime. After that, we have data transformation task, in which we use Ray task as a default compute strategy. And similarly, we use actor pool strategy for embedding-based key phrase filtering, which uses the sentence transformer model from Hugging Face. Similarly, we have actor pooling strategy for clustering key phrases that uses hierarchical clustering model from the scikit-learn's library. And we have the predictions inferences, and these are again stored in S3 bucket. So next, I'd like to talk about the results that we observed and comparison analysis between Ray and AWS Sagemaker. So we saw significant reduction in our ML workload runtimes. So these are some of the statistics that we observed. So in the case of key phrase extraction and ranking, we saw 4x returns. For example, Ray performed 4 times better than as compared to Sagemaker pre-processing job. Data transformation performed 15x better. Embedding-based key phrase filtering performed around 20 times better, and hierarchical clustering performed around 10.5 times better. In addition to solving our current limitations, like reducing the runtime and maximizing our CPU usage, it was relatively easy to scale ML workloads in a distributed fashion. For example, it's easy to customize compute resource assignments per task in ML workload, and it leads to better CPU utilization and prevents errors. And scaling from local to production, it was very easy for a data scientist, and building a distributed pipeline, Ray handles Python dependencies very seamlessly. So this is the little code snippet to show how Ray handles many things in a very easier fashion, so that it allows us to scale pipelines. For example, in this case, you can see we have a key phrase extractor class, and we are using a third-party library, PyTextRank. We are also importing a large model from Spacey. We have also defined our custom scrubber function, so that we don't want our PyTextRank algorithm to discard certain entities that we are not interested in. And if you can see, we are registering our custom scrubber function in Spacey and adding it to the Spacey pipeline. So it requires very minimal code changes in handling external dependencies. And if you look below, we have also divided the 2 tasks so that we can assign custom resource assignments depending upon the type of custom workload we have. So for example, in the post-processing step, we are using Ray task for the default computing strategy, and actor pool strategy for doing inferences with Spacey model. So that was our experimentation with Ray for scaling our ML workload. We are just getting started with Ray, and we also hope to adopt other ML workloads at Lexis. Thank you so much, everyone.